Is it on? Yeah? Can you hear me? Everyone? Cool. All right, so good morning, guys. Yeah, as you just heard, I'm going to talk about something slightly different than what has been going on for the past couple of days. I'm going to talk about synthesizing movement as an animator. So we have a slightly different approach. But in order to get started here, I thought, just to put it into context, I would like to introduce myself, just briefly. So I do a lot of different things, but my association here, my official association, is Technical University of Denmark. Currently, I'm doing my master's thesis in biomedical engineering, working in biomechanics and biped locomotion. But before that, I used to work in computer animation. So I have about 8 years of experience, professional experience in animation, where I worked primarily as the animator, which is the one that creates motion, but I also did some software development and a few other more technical stuff. So just to get started with that, I would like to show my animation showreel, which is some of the stuff that I've been working on in the animation industry. So everything here you see is created from the ground up using keyframes. Almost everything. There's one shot in the end, I think, which has some... Pardon?
What's the keyframe?
I'll tell you that in a second. Everything is made from the ground up. Let's just say that. Everything is created out of nothing. There's one shot in the end that relies to some degree on motion capture, but it's almost none of it. So the rest is just made up by me, pretty much. Let's see if there's sound. I hope so. Yeah.
Ubo, sharpen the battle claws. To arms. To arms.
Det går godt. Ja. Ud.
So, yeah. Thank you very much. So, what I'm going to talk to you about now is how is that actually being done? So how do you synthesize this kind of realistic motion? Not always completely realistic, but at least to some degree. So the outline of this talk is, first I'll tell you about how we're actually moving things around and determining the motion. Then a little bit about what goes into determining the right motion, like what is required to actually create these kind of movement patterns. And then I'm going to zoom a little bit out, trying to explain how we usually approach. So pre-production, you get a puppet, you have to figure out how is it supposed to move, how do you explore these motion patterns that you want to recreate. And then, yeah, I'll give a little example of how to do squirrel motion. Then I'll move on to the walk cycle, just to make it relevant. I thought that would be kind of relevant for you guys. So we have some animation principles describing the basics of a walk cycle, and that forms the foundation for how we go about doing that. And then some final thoughts. So creating movement, how we do it First of all, I'd like to point out that the job of an animator, that's the guy who moves things. So I don't, as an animator, create anything apart from just the movement. I get a puppet, so I guess calling us puppeteers would be also quite close to the truth. So I get a puppet similar to that one. So that's the squirrel from before, but without fur. And all the curves you can see around, that's the animation controls. So usually we move it around by selecting those controls, rotating, translating. And we do that by keyframes. So that, again, that's how we define the motion. So usually you would take the puppet, put it into a position that you want at a certain point in time. Then you would put a keyframe, which means at that point in time it's going to be this value. Then you go to another point in time, and you set another keyframe. And basically it works like this. So each node there on the curve, that's a keyframe. Time value correlation, and then you can have some. Usually we use Bezier curves to interpolate between them. And then doing that, then we create the motion simply by first blocking out very roughly where in space do we want the character to be at what time, and then iterate on top of that and refine the motion. So in order to do that, there's a lot going on in motion, and I guess this would be the crowd to know that. But it requires quite extensive knowledge of all the subtleties, because we literally don't get anything for free. Everything that was moving in my showreel, at least of the character, the animated characters, that's determined by me. Everything that moves is me controlling a keyframe that decides that movement. We don't do any simulations like that. So it's all, I have to know everything that goes on in order to make a movement look physical. So that brings me on to the second point, that we don't have physics. It's a virtual environment. There are no laws, really. All I can do is to move things around so that it looks like it complies with the laws of physics. That is particularly true in visual effects, which is my main area. So visual effects, that's when you do animation that has to merge with the live action footage. So in order for the audience to actually believe that the characters are in the same world, you have to move it around so that it looks like it complies with physics. And then accommodating expected behavior, that's an interesting point. And actually, I put this in after a talk with Greg Savicki, that how do you even explain it? I mean, we decide how stuff moves. There's no rule governing how stuff should move. So we basically decide that this thing looks nice moving in that way. And when we had the talk, it was basically about what do people expect out of movement. When you look at a certain object, you have a very good definition of how it's supposed to move. And as an animator, you simply have to understand what that expectation is and then move it according to that. And yeah, as I said, if it moves, it's intentional. So animators, we create everything. So the general motion, I mean, reaching of an arm, that's simple enough. But then all the correlated movements that goes on while reaching for the arm, the shift of weight, all the small jerks, and especially the acceleration of the arm, that's a very particular movement for it to feel real. Then sensitivity to cause of error. That's also I just put it in this morning. But basically, as an animator, all you do every day is to look at movement and determine why is it wrong and how can I correct it to make it more believable. I guess we would say believable. We would usually work with appeal. If one movement looks more appealing than another one, then that would be the target. But we can have a long discussion about what's the actual target of good movement. What is good movement? Obviously, it's different for robotics. So when you start a project, what do you need to do first? So for the squirrel, for example, I had to find out how the squirrels even move. So you understand the morphology, you understand the anatomy. How do you approach that? So first, we went out and found footage. So we recorded, I think, 2 hours of footage in a squirrel farm. And then it was just my job to look at the squirrel and figure out how does it do different things. So you look at how does it run, how does it walk, sit, stand, what are the key elements involved in that particular motion, how does it differ from other animals. Then you can look at the extremes and resting position. So what is the maximum range of movement for this particular animal? Which kind of movements does it use in particular situations? So when it's running, how far does it actually stretch out at certain points? What can you expect from the range of motion? And then resting position, where does it want to sit? What is the position that it prefers over others? And then a very important point is the timing. So we have to find out how much time does it use in different situations, what's the speed of motion of this particular animal. Squirrels move really fast, elephants move slower. So you have to figure out what is actually, which are the key positions, how long does it spend in these positions, how long does it spend in the transition, how does the interpolation look? And then you can look at effort versus relaxed. So how does this movement actually adapt if it's exerting high effort? How would it change when doing something that doesn't require much effort? And the same with the fast and slow variations. So other things like cycles. So in particular, relevant for quadruped walking. So you have the 4 cycles. We have actually quite a lot more. But 4 cycles of the legs, and how do they interrelate with each other? What's the cycle offset? And then you have the different weight distributions in the torso. For example, a dog would have a weight in the head, chest, and hip. And how do they work with the cycles of the 4 legs? So with that, then we start creating the actual motion. So here's a progression setup, I could say. So it shows how do we first block out the motion. So you define the general motion very roughly. You define where you want it in space, and you define kind of what is going on. And then you move on to refining it a little bit more to get sort of a smooth motion on some parts of the body. You then look into what's the physics, how do you insert physics so it looks like the weight is actually right. So down there, it's mainly the feet. So figuring out where should I put the feet in order for this physics to work reliable. And then in the end, polishing, putting everything in motion and making it all sort of stick together. So now I'll show you this again so you can appreciate the process that went into it. Play. So that's the result of 2 weeks of work. So it's not really a fast process. Another way to look at it. This is the other shot where you can see the animation controllers. So you can see how the animation controllers move around when you're animating them. So this is how I would look at it from within. I'm using Maya as the animation platform. This is how it looks for me in the platform. So it looks like a rat in that sense, but then you render it and it looks nice. To just give you one plot, because it's a technical presentation here, this is how the animation looks for that shot. So this is basically the graph editor in Maya. It looks like that. So you have the timeline at the bottom. You have X on the X-axis is time, Y-axis are values. And these are all the keyframes. That's all the curves that control this model. And just actually for the first time, for preparing for this talk, it was the first time I actually looked at how many channels or how many degrees of freedom does this character actually have. And I found out that I was animating 594 degrees of freedom. And I put 36,000 keyframes. So there's a lot going on there. And that's also why it takes 2 weeks to make something like that. And just to show a little bit more clearly, you can do a zoom in here. So this is how it looks. And now it's quite clear what goes on, right? Oh, sorry.
I would imagine that if you use Bezier curves between keyframes, and you have all these different degrees of freedom, that the curve in between keyframes does it necessarily respect what would be natural looking motion? Is that ever a problem?
Yeah. Okay, so the question was, because we're interpolating between keyframes with Bézier curves, then the values between keyframes would not always comply with physics. And it's a really good question. It's one of the very important parts of animation. So basically we try to put keyframes in the extreme positions, and then we make sure that everything in between still works. So what you do with keyframes is simply an approach to shaping the overall time evolution of a channel, of a degree of freedom. So we're consciously deciding on all the transitions, but we're defining it by keyframe.
Can I ask a question?
Sure.
At a keyframe, can you specify whether the tangent is specified or totally free? Do you have that choice in the?
It does. It's in the Bezier, those lines.
But if you have keyframes,
Yeah, okay, so if we control the tangents, there's the question. And yeah, we do. We have like a normal keyframe. You set a keyframe and it has an automatic, it sets the tangent automatically initially. And then you can go in and further specify it. If you want, in this particular case, a tangent that looks different, then you just go in and change it.
You can turn off the tangent.
Well, the tangent is, it's always on, but if
you can turn it off as a fitting parameter. So
Pardon?
for example, you can have a keyframe whose job is to be passed through in the most graceful way possible, as opposed to its job is to specify the velocity at that point. Like in Adobe Illustrator, you have these tangent line, and you can adjust the length of the tangent line, and you can make it something that well, actually, you can't turn it off the way I'm talking about. But in spline fits, you can have a point that you want to pass through, and you want to pass through in the most graceful way, or you can have a point where you specify the tangent. And two different specifications.
In this sense, you always pass through the keyframe.
You always pass through the frame.
You
The
always
question is,
keep-
you specify
yeah.
the tangent, or you can leave that free.
You can leave it free. You can do pretty much whatever. You can also change the weight of the tangents, but it's rarely used. We try to simplify the definition of motion as much as possible. So having normal spline interpolation with an automatic tangent, that's a good guess to begin with, and then you further iterate and you define the tangent how you want.
I think automatic tangent is what I call free.
Yeah, probably. Okay, moving on for that. Then I'll just go through a very quick crash course in how we animate walk cycles. So in animation, actually, walk cycle is one of the first things that you learn as an animator, but it's also considered one of the most difficult aspects of it. It's something that's really, really difficult to perfect because you have so many dynamics going on. And when if it has to look real and it has to loop, then you really have to get it just right. Also because humans are amazing at determining what is a healthy walk cycle. In particular, when you approach very anthropomorphic characters, then we read it every day. So what we have are basic principles. This is 2D. So you have these 4 poses, where the first and the last are the same. So you define it first. You define the walk cycle by figuring out where are the contact positions. So it's, heel strike, as you would call it. And then normally you would go about it putting in the passing position, so in the middle one. That's pretty much just straight in between the 2 contact positions. And then you further define the down and the up position. So like this. So you would decide on a path, and then you would block in these contact positions. You would figure out what is actually, where do you come from, where do you go, and you know kind of where all these should be because you know that the hind foot is at the same place at the front foot of the previous step, so that's easy. Then you put in the passing position. As I said, it's just in the middle of those 2, and then you add in the low and the high position. That is, you know it when it catches the weight after the contact position, then it goes up to the passing position, and then it pushes off. So you get a little bit higher at the end of the just before the contact. So in animation, we also like to play around a little bit. So depending on where you put the passing position, you can get very different strategies of walking. You get very different personalities. So you can play around with this a lot, and it's amazing how small changes in a walk cycle changes the personality. Yeah, so when you've defined these poses, and the next step is to define the timing. So in animation, how we define timing, like when you have the poses, meaning that you know where in space you want to go eventually, but you don't know when. So in animation, we decide that by figuring out which frame hits which pose. So here you have a walk cycle that passes through 13 frames. So the first contact is on frame 1, the last next contact is on frame 13. And then you figure out where is my passing position, where is my up and down. And then because there's a gap, so contact up to at the down position is from frame 1 to frame 4, then you have to figure out what are the in-between. So you have these 2 other frames that need to define the movement into this. And that's where you start figuring out the weight. So the way that you put these, it's not, no motion is linear in organic systems. So you have to figure out where to put it in relation to each other. What is the acceleration, deceleration? Where does it go fast? Where does it go slow? And you do that by defining how these in-between poses are. Yeah, then you can move on to twisting the body. How does the body twist when you walk? And you have like the opposite twist of the torso, and you have also the sideways twist for the hips versus the shoulders. And then eventually you put it in, and it should start automatically. Oop. No. Yeah, then you can get something like that. Doesn't particularly look very naturalistic. You would not see too many people walk like that, but.
How many keyframes?
What?
How many keyframes there?
I don't know. I actually don't know. But I mean, it's a cycle. It cycles on about 26.
In one step, how many keyframes? It's like 4 or like 30?
No. It would be more like a couple of hundred. Yeah, I think so. Yeah, because you put for each object that's moving, you have to shape the whole time evolution throughout the cycle. So it depends a little bit. Yeah, I would say probably a couple of hundred keyframes for this. If it's a clean animation, then you can make it quite messy, and then it would go into thousands.
Okay, for each body part, how many keyframes?
For each degree of freedom, how many keyframes?
Throughout a cycle like that, maybe 10, I would say, probably around 10, maybe a little more. I can look into that. But then, as another example, this is also animated, so there's no motion capture going into this. This is created from the bottom up with the basic principles. Thank you. And you can see it looks a little more naturalistic. So just to wrap up my final thoughts. What I believe is interesting as an animator in this business is the awareness of motion. So we have to be very aware of all the subtleties of motion. And I guess that we're one of the few disciplines that actually particularly focus on that. So we don't care about the function, we don't care about where it comes from, so it's a top-down approach to movement, and we simply have to recreate it so we know the outside. And then, yeah, it's important to fake physics. That's what we do. We move things like that. Yeah. And then I would actually just encourage more holistic observation of movement and a more intuitive approach to determining what movement is. Thank you.
Hello? We don't have any time for questions, so we're going. No.
So for me, it's really surprising that you have to live in this world of keyframes. Isn't it possible that you specify, like, in Euclidean space, a trajectory of the foot, and then you have like a simple inverse kinematics that solves all the keyframes for you?
A lot of the approach in animation is based on the fact that it's based on artistic expression, so body language, and we need to find a way to explain it in a way that also works with animators' way of thinking about movement. So this is kinematics. We just set out which kinematics do we want at what time.
But the kinematics of every keyframe, and not like
Yeah.
Repeat.
Kinematics of every keyframe? Yeah.
He says you could have the physics do a whole trajectory and then build everything around that.
Yeah, the problem with that is that in order to use any physics simulation, you would have to put in a lot more effort into designing the character. And if you start using physics, then you're also limited in the creative process. So it's something that we pretty much just disregard in this sense, and we just put it on the shoulders of the animators.
No, but you can still live in the kinematics world, and you just specify the trajectory of the foot.
Ah, yeah, okay.
And you create the joint angles for each of the
Sorry, okay. We do that. So basically,
he suggests doing inverse kinematics. You specify the end of the robot arm, and all the joint angles get calculated rather than the
we do that. We do that actually on feet in particular because they have contacts. So it's very easy for that particular situation. Then we use IK and we animate the end effector only.
Inverse kinematics, IK.
Inverse kinematics. Sorry. And then we, for example, we have a controller for the center of mass, and we can move it around, and the feet sticks to the ground. But for arms, for example, we would not use it for arms because you get a very unnatural motion if you move an end effector around. Normally, you swing your arms. Your arms tend to use to move in arcs, not in like you don't.
If you
it's a tricky thing
if you just specify the endpoint for the hand, it might do some funny kinematics.
Yeah, you get weird motion that doesn't look natural if you animate in inverse kinematics of the arms, and then you have to compensate for a lot of the dynamics that you get more for free if you.
Let's go on to the next question. Let's go on.
So
talk later.
Put up your reference slide for reference 3, I think you said. Noah?
Reference? What do you mean? Yeah. Okay. I forgot.
Noah?
Reference.
So first of all, this is great. My high school friend was an animator. I mean, not an animator, a puppeteer. And the way he described movement was really fascinating. And so this is great that you came and gave this. But it seems to me that physics would actually not be the right thing to use because, as you said, you kind of want to make it unrealistic in a way that exaggerates certain things that still feels natural, but yet kind of emphasizes something in the movement that wouldn't come out of an optimized simulation of like walking or something. You're sort of adding things that are colorful in just the right way, a little anticipatory motion.
What's your question, please?
Physics. What is this? So is this? I mean, people must have tried this in your business to sort of bring more simulation into it.
Yeah.
And it probably just makes pretty lousy animations.
So the question is if anybody has tried using simulations in animation and why we don't generally do it. And I would say the point is that it's such a creative process that you listen to a director who says, go over here and look happy while you do this and this and this, and then go over here and then you take up this ball and throw it at that guy. And it has a lot of subtleties to it, and I don't know how you would approach that with physics and simulation.
But if you came to dynamic walking religiously, you would have seen several talks about this over the years.
But my belief is, it's dangerous to say.
Russ?
How much does stride-to-stride variability, is that one of the principles that's making it look more realistic? You have to make every step look different?
Yeah.
Repeat the question.
Stride variability, if we include stride variability when we animate walk cycles. So generally how we would do it in particular in bigger productions, we would make a library of very clean cycles, and then we would import those cycles and fit them to a trajectory, and then we would fit them to give the personality that we want in this particular situation. Because there is a general tendency for the same character to walk in the same way, but you also have, in this shot he has to walk in an angry way, in this shot he has to walk in a happy way, in this shot he has to stop and maybe just take a few steps on the side, and then you just put in the building blocks, and then you fit it to each shot separately.
Does it look unnatural if you're perfectly periodic though? Does the human eye say that doesn't look like natural walking?
You have to put you just repeat the question.
Yeah, okay. Does it look unnatural if it's just the same cycle repeating? I wouldn't say really that it does look unnatural, but in most situations you don't just walk in a straight line, you're usually doing something else. And then whatever you're doing at the same time works with works with how you're moving.
How are we doing time?
Yes,
One last question.
20 seconds.
So, instead of applying physics to animation, do you know if animation has been applied to physics? So basically, you take your super many degree of freedom kinematic models, apply physics to that, and create like robot control strategies out of that. Because you're capturing nuances that researchers may miss.
Okay, so,
Can you repeat that?
yeah. Am I aware of any situation where animation techniques have been involved in informing on robot kinematics or
Physics models that feed into like robot control strategies.
a physics model that lead into robot kinematics control?
Animation strategies. So
Yeah.
he's asking, could we use you to help us? Or have you know what you're doing?
Okay, translated by Andy. Yeah, could you use me to help?
Could we think that you think that you think that you
Yeah. I'm not aware of any technique so far, but I can just show you one slide where I used it myself to design a robot. Actually, I put it in, but I took it out because it's robotic related. But this little guy, that's a powered passive dynamic walker, which I designed by animating the motion that I wanted to get. And then I fitted in the dynamics. Yeah, I built the dynamics that I kind of felt was in my motion, in my animation. And then I iterated a lot of times on looking at how it actually behaved, filming it, recreating it in Maya, tweaking some of the dynamics, printing out. So the feet are 3D printed. Printed out those until I got something that I actually liked better. I have this, I'm going to show it at the hardware demo later. If you want to play, it's like QWOP. You control it through your mobile phone.
Okay. Yeah, the short answer.
Yes. So the answer is yes, but this is the only example I'm aware of. And
But just for myself, I'm thinking we should be talking to you, actually. Are there any more questions? People seem really interested in this. Okay, back there. Go ahead. Do you have a microphone?
Thank you. So my question was about the scalability of this. So I'm just thinking of Ratatouille movie, for example. So if you create motion for one, I don't know what you call it, like animal, squirrel. So is that scalable to, I don't know, different heights or weights? Or, I don't know, like weird leg size, but still the other parts of the body are the same? Could you do that?
There are tools for remapping motion onto different morphologies, but usually they don't work. Or you get a good estimate, and then you put an animator to fix all the issues. So generally the answer is no. It's very tightly controlled. As I said, we're really, really good at determining the issues. I work with some motion capture where the motion capture was recorded on a normal human being, and then it was mapped onto these huge green Martians with 4 arms, and that looks horrible. I mean, you cannot use that at all. It's a completely different physics. So you had a lot of animators to tweak that motion, and eventually we actually just wiped all the motion capture and created the motion from scratch.
I'm going to allow myself to ask a question. So in motion capture, after you collect the data, you could do least squares to constrain the motion capture to respect the kinematics of joints. You can add a post-processing to motion capture that it has to be the closest thing to what you see on the camera that obeys the laws of physics. I would think that they would add to Maya a tool which is obey center of mass physics. Take this arm and minimize you add a post-processing layer to what you have to make it, and maybe even give you a knob to turn that to go towards physics and beyond, or that would be a post-processor for your thing that might tune up things a little bit. Is that a tool that exists?
I don't know about that particular capability, but I mean there are definitely tools that try to approach the final product, but
finally obey the laws of physics.
No final what's going on the screen in the movie.
You could say, I would like to take what I have and find the closest motion to that obeys the laws of physics. And then you could say, obeys the laws of physics with bounded ankle torque, obeys the laws of physics without bounded ankle torque, obeys the laws of physics for center of mass motion only, and so on.
Yeah. You could probably do that, but again...
But it's not part of the tool.
No.
It just feels like it should be
I've thought about it actually, but in my opinion, it would only be an approximation of the final product because there are so many things that we need something on
just
screen.
a tune up here, just a little tune up at the end.
No, it would be a tune down normally.
Okay. Okay.
Hi. So with walking humans or animals like squirrels, the audience has a notion of natural, and that's what you're working with. But what about, let's say you want to build an animal that's three-legged on Mars or somewhere, so the audience has no notion of natural, and what are you trying to emulate then?
Repeat the question in your own language.
Okay, so how do we determine how a morphology would move that doesn't exist in the real life?
Yeah.
It's a good question. It's part of the whole animation process. Usually there's a lot of work going into defining those kind of things. In particular in big projects, you have a team of animators.
Let's switch the computers here.
You have a team of animators that work on that particular issue. Wait.
Okay, so now really one more question. Yes.
I probably didn't answer correctly, but I can tell you more in a bit.
So, at least in neuroscience, how people say one of the theories behind how you control like hundreds and hundreds of muscles is the idea of motor primitives or synergies, where instead of controlling hundreds and hundreds of muscles, you control 5 parameters that weight the individual muscles. So some sort of dimensionality reduction of what regular movement is. So in animation, for example, is that a thing? Is that a way that you approach it?
Repeat the question in your own language.
In my own language, it would be kind of, do we use muscle activation at all for?
Oh no, not muscle activations, but do you do dimensionality reduction? So instead of controlling, 500 different body parts, is there some relation between them that's natural that you can reduce that parameter to like 5 parameters that can?
Yeah. Okay.
Motion?
So setting up a model to be animated, that's an art by itself. So that's called rigging in this industry, and you generally try to set up as much automation as possible to make the animator work as little as possible, but you always allow for an override of that because you assume some things and then you get in a situation where you want to break out of that, and that happens all the time. So we try to automate as much as possible, setting up some constraints and relations, and then we just layer on top the subtleties.
Can you put a number on that? You had 594 that you could control. What's the lowest number that they give you if you just wanted to barely make it work? Like what's the lowest number of primitives that will make something kind of function if they do a good job?
Well, you could see the progression shots I had. To begin with, the first movement, that was pretty much just the center of mass and the 2 feet that I moved around. The rest was static. Then I get a good idea of where I want to be. And then you add more controllers. Then you add maybe...
But nobody does like principal component analysis and takes the first 5.
It's a very non-analytical area.
Okay. The program is a little... Thank you very much.